Hi, my name is Ron Lynch. I do web handling training and consulting. This presentation is about web tensioning, the placement of driven rollers and idlers in a web path, selecting the right tension for the web, and how to select the velocity for the driven rollers. Tensioning is the first thing you have to get right when you are engineering a new web path, engineering the equipment, making changes to an existing web path, changing raw materials, or solving a web handling problem. Wrinkle-free converting, tracking stability, the reliability of transformations, roll winding quality, all depend on consistent tension at the correct level in each span of the path. Web handling does not have a universal language, so we'll spend some time in this session to pin down the definitions that I use. Width and length are obvious, and we're going to use L sub 0 for the relaxed length of a piece of web and W sub 0 for the relaxed width of a piece of web. And this can be in inches or millimeters. The 0 subscript will be for the relaxed condition of the web. So when we apply tension force to a web, the web gets longer. So we'll have a stretched length L sub n of the web under tension. Tension can be in pounds or newtons, and the n subscript will indicate something in a span in the web, in the nth span of the web. Classic engineering strain is if we take a web, we apply tension force to it, it gets longer. And so we have a stretched length L sub n, a relaxed length L sub 0. We can calculate strain as the difference in length, L sub n minus L sub 0, divided by the relaxed length. Now, this comes in two forms. We've got a decimal value formula, which is what we'll use in all of our calculations. And you can multiply that by 100%, which you commonly hear in some conversation. Now, you got to be careful. These can be used interchangeably in conversation. In some formulas outside of this presentation and outside of my classes, they'll use the percent formula in calculations. But in this presentation, in this class, we will always use the decimal value. Now, tension and strain are two different things. Tension is a force and has to do with how the web interacts with the things that it touches: rollers, air, gravity, parent rolls, etc. Strain has to do with dimensional changes in the web, stretching, curvature, things like that. And so they are two different things, and we'll have to keep track of both of them. They're related by modulus, but they can have two separate criteria for what's good and what's bad. There are several things that get called modulus. The first one we'll talk about, web modulus, E sub w, is the slope of a plot of tension and strain. So tension force and strain. And so web modulus is the change in tension divided by the change in strain for the slope. So it'll have the units of pounds or newtons depending on your force units. And the way we use it is the tension force is equal to the strain applied to the web times the web modulus. Or the strain that results is the tension force divided by the web modulus. Now note that E sub w, web modulus, applies to a given width of web. So if I have a 1 meter wide web and it has a web modulus of 10,000 newtons, a 2 meter wide web is going to have a web modulus of 20,000 newtons. And so web modulus will increase and decrease with the width of the web. But it is a very convenient and intuitive thing to work with, which is why most of my calculations will involve web modulus. So this is the fun part of this presentation, so you need to pay attention to this. The next few slides are talking about how tension is generated in a web, and they're key to understanding web tensioning. And so we're going to go through this, and if you have any questions, you can ask after the session or call me up or send me an email if you have any questions on this. So imagine we've got a web path with 4 driven rollers here. I've shown them as nip, but we're just assuming they're in traction. Okay, I have a strain of 0 approaching the first one. We have velocities of 10.0 feet per second, 10.2, 10.1, 10.3 feet per second. This could be inches per second, it could be meters per minute, it doesn't matter what the units are. What we know is in steady state, web will run through a line and do that for hours on end, hopefully. What does it mean to be in steady state? Well, what it means is that the web entering a span in a given length of time is matched by an equal quantity of web that's leaving the span in the same length of time. Now, if we look at the first web in this example, we've got a roller going at 10 feet per second, and the web approaching it is at zero strain, and so that roller is drawing in 10 feet of relaxed web per second, feeding it in to that first whole span. Now the roller at the end of that span is going at 10.2 feet per second. And so what has to happen is that 10 foot of web that we feed in there gets stretched out to 10.2 feet in length, so that what feeds into that span can feed out of that span based on the speed of that roller. And so what we know is it's stretched to 10.2 feet in length. And we know about the strain then. Its relaxed length was 10 feet, its stretched length is 10.2 feet. We can calculate that it has a strain of 2% in it. This can't be violated. If that 10 foot length was only 10 foot in length, the roller would take out all of that 10 foot and a little bit of the next one. And so it would eventually nibble away at the web in that span until it pulled out enough that it was stretched to 10.2 feet in length. So we feed 10 feet of relaxed web in, we feed 10 feet of relaxed web out, but that 10 feet in that span is stretched to 10.2 feet in length. Now, if we look at the next span then, we're feeding 10.2 feet in, but this next roller is only going at 10.1 feet per second. Our web can relax back to 10.1 feet in length in this span, and so it does have to be able to suck itself back together a little bit and relax back to 10.1 feet in length. Now, it's still the original 10 foot that we fed into the first span that fed out of the first span into this one, and so we can calculate its strain based on that original 10 foot of length and find that it has a 0.01 or 1% strain in this span. And if we move on to the next span, 10 foot of length feeds out of the previous span into the third span, gets stretched here to 10.3 feet in length, we can calculate a strain of 0.03 or 3% strain. So it is that same 10 feet of web that gets fed into each span, stretched out to match the speed of the roller, but fed into the next span all the way through the end of the path. And what comes out the other end of the path is 10 feet of relaxed web per second. So what flows in flows out for each span. Now, what falls out of this mathematically, and we're not going to go through any derivation, is the velocity of the web in any span divided by 1 plus its strain is equal to the velocity of the web in any other span divided by 1 plus its strain. And so the velocity in span n divided by 1 plus the strain in span n is equal to the velocity of some reference roller divided by 1 plus the strain, the reference strain in the span approaching that roller. This is known as the strain transport formula. It is the one thing you need to understand thoroughly to understand tensioning in a web path. You can't violate it, doesn't matter what the web is, its velocity divided by 1 plus the strain is constant throughout the web path. Now, this formula breaks down into two flavors. We got a strain flavor and a velocity flavor that are shown here at the bottom of this slide. So, let's see how we apply this to a web path. So I've got a web path here where I have a parent roll, an idler, a dancer, a load cell, followed by a driven roller, followed by a black box, and we'll fill it in later. Another driven roller, velocity 8, another black box, and another driven roller, velocity 13. So first thing we do here is we can calculate the strain in span 3 as 100 newtons divided by 10,000 newtons gives us a strain of 0.01, 1% strain. We can then leap ahead to the next driven roller, velocity 8, roller 8, and calculate the strain that's going to result there. And so we use the strain flavor. And as the velocity of roller 8 divided by the reference times 1 plus the reference strain minus 1. And we can fill in those numbers and we can calculate the strain in span 8 as 0.02, 2%. And then tension is that 0.02 times our web modulus of 10,000 newtons is 200 newtons. And so we can calculate. What we've done is we go from driven roller to driven roller to driven roller. First we identified where our references were, tension 3, velocity 3. Then we went to velocity 8, and then we went to velocity 13. What's in the black box doesn't matter. The strain and tension in span 8 depend on the references and the velocity of roller 8. So we've got the two formulas here, a velocity flavor and a strain flavor. Now, if I had said I want a strain of 2% in span 8, what speed do I need to run it at? I could have solved that with the velocity formula. And so you need to apply whichever one you need for whatever question you have. Now we go to the next driven roller, velocity 13, roller 13. It's got a velocity of 40.4 meters per second. We've got the same reference velocity and the same reference strain that we had from the previous example, V3 and T3, or strain 3. We can plug these into the strain formula again, and we can calculate that the strain in span 13 is going to be 0.01, and the tension will be 0.01 times 10,000 newtons, will be 100 newtons. And so again, we leap ahead, driven roller to driven roller, skipping the black box in between. And if we had more driven rollers, we would just keep going with the same thing at this point. Now we're going to look at idlers. Their job is to change the direction of the web up or down, or occasionally to control its position, as in a backup roller for a process. Idlers have resistance to rotation. We'll call that drag, and this is caused by their bearings. Now, the drag is a function of the rotational speed. Typically for bearings, the faster they run, the higher the drag. And what we're calling drag here is the force that's needed to be applied to the surface of the roller to keep it spinning at run speed. And this drag comes out of the web and comes out of the web's tension. And so drag represents a tension difference that we're going to see across the roller. It's the resisting torque divided by the radius of the roller. And in steady state, drag is equal to delta T is equal to the tension downstream minus the tension upstream. It'll have the same units of force that we use for tension, so pounds or newtons. And it can be different for different rollers, even with the same bearing if they have different radius. And so drag is the force that you have to apply to the surface of the roller to keep it spinning at line speed. Now, idlers also have inertia. But that only applies during acceleration and deceleration. So we're talking about steady state here, so the inertia is not a factor at this point. So if we look at this then, and we use this in a calculation, drag is a force, and so we can subtract it or add it to web tension as necessary. And so downstream tension is equal to the upstream tension plus the idler drag, the delta T, or upstream is equal to downstream minus the delta T. We're assuming no slip for now. We'll talk about slip later. In this example, we've got an idler with a 5 Newton drag. We've got a downstream tension of 200 newtons, and we want to find the upstream tension. And so upstream is equal to downstream minus the delta T, or the drag. It's equal to 200 newtons minus 5 newtons, or 195 newtons. Now, if we go back to our web path and we've replaced our black box with 4 idlers here, the strain and tension in 8 is still 200 newtons. That depends only on the velocity of 8 and the references. And so adding idlers here is not going to change the tension or strain in 8. And so we got 200 newtons in 8. How do we find 7? We subtract out our 5 Newton idler drag. And so it's 200 minus 5 is 195. And then we got 190 in 6, we've got 185 in 5, and we've got 180 newtons of tension in 4. And if we wanted to, we could calculate the strain at that 180 newtons of tension. If we look at the next spans, 9 through 13, We've still got the same 100 newtons and 13. That doesn't change. It depends only on the speed of 13 and the references. And so 100 newtons minus 5 is 95, minus 5 is 90, minus 5 is 85, minus 5 is 80 newtons of tension in span 9. And so we leapt ahead to the driven rollers, and then we subtracted out the drag of the idlers, working back upstream from that. So let's see what happens if the drag for idlers 4 to 12 increases to 20 newtons. Well, what happens is span 8 is still 200 newtons, and now span 7 drops down to 180. Span 6 is 160, span 5 is 140, and span 4 drops down to 120 newtons of tension. And so what happens to the tension in span 4? It goes down. More of the available tension was eaten up by the idlers. And so of the 200 newtons that was available at the driven roll, the idlers ate up 80 newtons of it now, and there's only 120 newtons left over. What happens in spans T9 to T13? Well, if only spans 4, 5, 6, and 7 changed, nothing would happen in 9 through 13. Why? Because you still have the same quantity of web passing roller 8, and so the next spans don't see any difference. They don't see any change occurring in the flow that's entering that zone. And so the tensions in span 13 depends only on the speed of 13 and the references, and so there's nothing going to happen in those spans. However, if 9, 10, 11, and 12 increase to 20 newtons, then we will see a change. And so we'll still have the same 100 newtons in 13. 12 will drop down to 80, 11 will be 60, 10 will be 40, and 9 will be 20 newtons. And so the 100 newtons available is unchanged, but the idlers eat more of it and only leave 20 newtons left over in span 9. Now we're going to talk about sliding contact. Okay, so the job of sliding contact is again to change the direction of the web, or sometimes are used as part of a transformation to do something to the web. Examples might include turn bars, bow bars, D-bars, slot coders, various kinds of applicators for things, folding boards. A stuck idler is sliding contact and could be treated the same way as an intentionally not turning bar. The tension is normally governed by what we call the Capstan formula, which says the downstream tension is equal to the upstream tension times e to the mu theta, where mu is coefficient of friction, theta is the wrap angle in radians. In steady state, then, tension downstream is always higher than tension upstream at any kind of sliding contact. Now, air flotation devices, we're not going to talk too much about them here because they really have very small effective tension on the web. There's no hardcore formulas for calculating it. They have no inertial effects on the web. And so we're not going to, that's another whole class as to how to deal with air flotation. So we're not going to do that here. So the Capstan formula, the way you commonly see it written, is the tension ratio, tension high over tension low is on one side. On the other side is the e to the mu theta value. E is the exponential base that you'll find on your calculator. Mu is the coefficient of friction. Theta is the wrap angle in radians. And so what you want to know about this is the e to the mu theta is a property of the system, the coefficient of friction and wrap angle. And it will calculate a tension ratio that's the high tension divided by the low tension. If your e to the mu theta value is 2, for example, if your high tension is 100 newtons, your low tension is going to be 50. If your high tension is 400 newtons, your low tension is going to be 200. You'll still have that same ratio. That's determined by e to the mu theta value. Now, the Capstan formula, TH over TL equals e to the mu theta, again comes in the two different flavors. The high tension is equal to the low tension times e to the mu theta, or the low tension is equal to the high tension divided by e to the mu theta. What this means is if you know one side, you can calculate the other. So, an example calculation here. We've got a classic turn bar example where we have a T6, the downstream tension is 190 newtons, coefficient of friction 0.3. Wrap angle is 180 degrees or pi radians, and so we need to find the upstream tension, T5 in this case. We've got our Capstan formula. We can solve it for the upstream tension. It's equal to the downstream tension divided by the e to the mu theta value. If we plug the COF and wrap angle in here, we find e to the mu theta is equal to 2.57. And so our 190 degrees divided by 2.57 is 74 newtons on the upstream side. And so we've lost, what is this, almost 120 newtons of tension sliding the web over that turn bar. So definitely idlers are much better in lower drag than sliding contact. So if we go to use this in a calculation, then we're back to our web path. We've got our same 200 newtons in span 8. We subtract 5 newtons and we get 195 in 7, 190 in span 6. We have the same wrap angle and COF as we had in our example, so we take our 190 divided by 2.57. We get 74 newtons in span 5. We'll have 69 newtons in span 4. And so that's how it would fit. It doesn't increase what's going on in span 8, but it consumes more of the web's tension and sliding contact, and we have less left over in span 4. If we do the same thing in 9 through 13, we've got our 100 newtons in span 13, 95 newtons in 12, 90 newtons in 11. We divide that by the 2.57. We get 35 newtons left over. And then we have 30 newtons left over in span 9. Roller traction. A second use of the Capstan formula is looking at the traction of webs on rollers. So far we've assumed no slipping, and now we're going to actually go back and confirm or deny or find that that is not the case. So friction drive rollers, that is SRAPs, single driven rollers, they control the velocity of the web only if they're in traction, that is, if they're not slipping. For driven roller, either the upstream or the downstream span can be the higher of the two. So TH over TL doesn't say downstream over upstream. It just says the high tension side divided by the low tension side. And then lastly, nips are assumed not to slip. The Capstan formula doesn't apply directly to nips. For all practical purposes, if they're well designed, the web does not slip through a nip. Now you can have brush nips and gapped nips and things like that, and those are all special cases that we'll not cover here. So Capstan formula can be used to make sure that you're not slipping on your driven rollers. It can also look at idlers and make sure that you're not slipping on your idlers. And you can use the second use then of the Capstan formula is to do slip checks on your rollers. So if we look at a roller here, for example, a couple of points to make. If you have an SRAP, two driven rollers in a row with the same wrap angle, the same coefficient of friction of web across those driven rollers, you can simply add the wrap angles. And so we've got two rollers with roughly 180 degrees of wrap on here, so we can assume a total wrap angle of 360 degrees, or 2 pi radians. So for the example on the right-hand side, we've got 200 degrees of wrap on this roller. We've got a coefficient of friction of 0.5. We can calculate an e to the mu theta value at 5.72. Our tension ratio is 150 newtons divided by 35 newtons, or 4.29. And so our actual tension ratio, 4.29, is less than our e to the mu theta value of 5.72. So as it's shown there in this example, it won't slip. However, if our low tension would drop to 25 newtons, our tension ratio, TH over TL, would be 6 to 1. And a 6 to 1 tension ratio with an e to the mu theta value of 5.72 would slip. So with 35 newtons, yeah, it's not slipping, but it is right on the edge of failure. Typically when we do Capstan formula and wrap angles and coefficients of friction, we will apply a safety factor in there, typically 2, There is no hard rule of where you apply it, how you apply it, or what that number should be. It's just you want to make sure that you typically don't slip on those rollers. And so give yourself a lot of leeway there. So if we go back to our web path now, we've got all friction rollers in place. And so if we look at our first SRAP, which was our reference roller, we've got 100 newtons on one side, we've got 69 newtons on the other side. Our tension ratio is 1.45. Our e to the mu theta value for the wrap angle and coefficient of friction that we specified for it is 4.11. So this one is definitely not going to slip. We've got almost a 3-to-1 safety factor there. And that's what you want as a good safety factor on your master roller, your references, because you really don't want to slip there, because that would upset everything downstream. Now, if we look at our second roller here, we've got 200 newtons on the upstream side. We calculated that we only had 30 newtons on the downstream side. That's a TH over TL of 6.67. That is definitely bigger than the 4.11. So our capstan formula is not satisfied. That roller is going to slip. And we'll come back and talk about that in a second. We can also apply this to idlers. And so we'll take just one idler here. We've got 30 newtons on one side. We've got 35 on the high side. Our tension ratio is 1.17. Our e to the mu theta value is 1.6. So that roller is not going to slip. And you can go through and do every roller in the web path if you want. But typically you can spot check a couple and see if they're going to slip. But generally, for this example, we'll just do the one idler. So we've got an SRAP in the middle of the web path that is slipping. Now, a line will run like this, okay? It's just that it won't be doing what we thought it was doing, and it may not do whatever it's doing consistently. If we look at this then, it is slipping. We can look at our capstan formula. There's 4 variables in there, TH, TL, mu, and theta. And we can play around with those. We could say, you know, what makes TH smaller? What makes T9 larger? How do we get more coefficient of friction? Well, we can spend money for a fancy roll coating. Or we could change our wrap angle. You can change the orientation of these things. You can get almost 540 degrees of wrap out of an SRAP. So there are 4 variables to play with. Now, my answer to this question is make T8 smaller. If we can get away with a lower tension in any span, lower tension is generally better. And so that is how I would solve that. So if we look at our capstan formula then, we used it to do a slip check on driven rolls. And so we want to make sure that our TH over TL is much less than our e to the mu theta value. We used it to do a slip check on an idler. TH over TL needs to be a little bit less than our e to the mu theta value. Slipping on an idler is generally not fatal. Slipping on a driven roll is a bad thing. Last thing we used it for was the actual tension ratio across the deliberate sliding, a turn bar, bow bar, something of that nature. And there it's an equality, TH over TL equals e to the mu theta. So 2 different uses, don't confuse them. When you're using it to look at driven rollers and idlers, you've calculated those tensions using strain transport formula methods, and this is just to check to see if it really can do what you say. Turn bars, it's used as an equality. It actually calculates the tensions. 2 different uses. So formula summary then. We've done all of this so far with 4 formulas. Tension equals strain times web modulus, the strain transport formula, the idler drag formula, and the capstan formula. Just about anything that you do in web handling can be modeled with these 4 formulas in steady state. And so you might modify them a little bit for a very specific case, but especially the idler drag and the capstan formula, but 4 basic formulas cover just about everything you can do in web handling. Okay, so now we know how to calculate the tension and strain in each span. Now we got to figure out, well, what tension do we want? And we start by asking what's too high, what's too low. The general industry guidelines for tensioning is it should be about 10 to 25% of the tensile strength. But that's not always the best rule, and it can be very vague for optimizing the design. So we're going to try and pin that down a little bit better here. Now we're going to start by imagining that there are some maximum and minimum failure values that we never want to cross. You know, bad things happen. We just can't run there. We wouldn't sell the product if we could. And so we're going to identify those, or at least as well as we know how. Then we're going to keep in mind that tension and strain have separate criteria for their maximum minimums. Okay, tension is a force. It has to do with how the web touches things. Strain is about dimensions and what's going on inside the web. So there can be a lot of factors that go into these failure criteria. I'm going to pick some of the more common ones, but you may have some specific things in your process or machine that are in addition to the ones I'm going to talk about. So on the high failure side, for strain, it's damage to the web. And so you're going to ask yourself, what is the highest strain that I can apply to my web and still call it good material? At what point is my customer going to complain that I have damaged it, overstrained it, reduced its properties, or something like that? And so damage to the web. And you have to decide what is damage to your web. Some webs, it may not matter much what you do to them. And others, it could be very touchy. Tension on the high side is actually damage to the equipment. Most webs run over rollers, and most rollers deflect when you apply tension to them. And so at some point, you're going to deflect rollers enough that you get into either tracking or wrinkle problems. And typically, you'll design your rollers to support a given amount of tension in the range that you expect to run. And if you exceed that tension, you may get too much deflection. So that's what we'll call damage to the equipment. Now, in some cases, you might also damage the web. If you pull your web down too hard against a grooved roller or a textured roller, you might make lines or dimples in it. And so you can create damage to your web from too much tension on some types of rollers. Now, low failure criteria, strain can be loose edges, maybe from a cambered web or a web that's got some waves in it and things like that. Can be loss of traction with idlers. It can be sag and long spans. Now, if we think about camber, okay, cambered web is a curved web. You can calculate a radius of curvature from that. And from that radius of curvature, you can calculate what's called the critical strain and the critical tension. At a tension less than this, your web's going to have a loose edge. At a tension higher than this, it's going to be somewhat straight and flat. And so there is a critical tension that we can use as a low tension or a low strain failure criteria. If we look at idlers, I find this an interesting one. So we've got our idler formula. And if we plug it into the Capstan formula, in order to maintain traction with an idler, our low tension side has to be greater than the drag of the idler divided by e to the mu theta minus 1. What's interesting about this formula, it says that the lower the drag of the idler, the lower the tension you can run. And so if you do run very, very low tension in your path, you need to have very, very low drag idlers. But anyway, it dictates a minimum tension based on the drag of your idlers. Anything less than that, you can't maintain traction. You're going to slide. Sag and long spans. Now, if you have a very heavy web or very long spans, this could be an issue, but it does dictate a minimum tension. How much sag is acceptable? My rule of thumb is 0.5% of the span length. And that is a rule of thumb. There's no science to that one. Within these failure criteria, we want to come up with a narrower design range that we want to try and run in for normal conditions. Okay, we don't want to run right at the limits of failure because that's only going to get us into problem if we have variation. And so hopefully if we have a tighter design range, variation will keep us out of, still not get us into trouble. And so there are some constraints on the high over low tension of our design range that we have to think about. One is viscoelastic recovery. When you stretch a web and try and let it recover, it doesn't instantly recover to its original relaxed length. It takes some time to suck itself back up. We can't typically take huge tension drops over driven rollers and expect the web to fully suck itself up. My experience with a lot of webs is they'll typically do about a 6-to-1 recovery. If you stretch them and relax them, the instantaneous recovery will be about 6-to-1. So if I stretch it to, let's say 1.2% strain, it'll relax back to 0.2% strain, about a 6-to-1 recovery. So you can't ask them to do any more than that. Width change. Big tension drops over driven rollers can lead to wrinkles. At high tension on the upstream side, the web is neck down. You go over a roller, you drop it into a low tension zone, you'll see a lot of waves and troughs because the web gets wider, but the edges don't move apart. So all that extra width becomes troughs. And so big tension drops over driven rollers can create wrinkles. Driven roller traction. Capstan formula, TH over TL, can dictate that. And the available motor torque. If you have really high tension, really high modulus webs that run high tensions, you can't take big tension drops. You may not have sized your motors big enough to be able to do that. And so we've got viscoelastic recovery, width change, and driven roller traction. Now, going back to the viscoelasticity, my typical experience with webs is they can instantly do about a 6-to-1 recovery. And so you don't want to design right at the limit of failure. And so I typically say take a tension drop no bigger than about 3-to-1. Give yourself a 2-time safety factor here. Your webs may be different, don't know. Same with width change. If you have very narrow webs, there's typically not a wrinkle problem. If you have really wide webs or webs that neck down a lot, you could have more issues even at 3-to-1. You can design driven rollers wherever you want them to be. There's no reason to design a roller that's got a 50-to-1 e to the mu theta value because typically your webs can't handle it. And so you need to look at what your webs can do and give yourself a generous safety factor over that. And available torque, again, you can size it for whatever you need for your web, but there are limits. And so we might have a typical TH over TL for our design range of 3-to-1. So what do we do with that? I can put all this together in a span plot. And so I've got an upper failure criteria, I've got a lower failure criteria, and I've got a design range that right now I've centered in my web path, but I can adjust that later. And what I'm going to do is I'm going to plot this span by span on my my span plot here. Now I can do this all in strain or I can do it all in tension. It doesn't matter. You can use modulus to go one way or the other. It's whatever you're comfortable with. I usually think in strain value, but it can go either way. First thing I do then is I put the first span in here. Okay, somewhere in the design range, towards the bottom of the design range. Now there are some special first span requirements. Have to have enough tension to overcome blocking. Okay, blocking is the tendency for layers of the web to stick together. Now, if you have just general webs where the web sort of falls off the surface of the parent roll, again, my rule of thumb is about 15 newtons per meter of web width. Can be higher if you have some camber, but just for blocking purposes, 15 newtons per meter. If your web does block, if you have something that's got adhesive on it, or for some reason layers want to stick to each other, you may need to have a much higher tension in that first span just to peel the web off the parent roll. And so again, you have to know about that. The second thing is you have to have enough tension to survive a splice and not back wrap the parent roll. Every splicing method is pretty abusive to web tension, and it can be all over the place during a splice, depending on how well you've set it up, the nature of the splice, the type of splice that you have. But there's probably some place where the tension will spike up, and there's probably some place in there where it can drop off very low. And so you need to know where that is, obviously, and have a first span steady state requirement that's high enough that you don't go to zero tension and back wrap a parent roll. So there are some first span things you have to think about that don't apply to any other span. So if we look at our second span in this process, it has to have a tension that's higher than the first span by the amount of idler drag in between. And so if I look at the third span, it's going to have a higher tension yet by the drag of the idler between the second and third. Now, if I just kept adding idlers here, and I added a fourth idler to it, then the tension in that fourth span has to be higher than the tension in the third span. But if that takes us over our design range limit, I probably don't want to do that. So instead of a fourth idler, I'm going to add a driven roller in there. And what that allows me to do is that allows me to start over in the next span down at the bottom end of the design range. So my fourth span starts over near the bottom end or at the bottom end of the design range. Okay. And then I can, keep adding rollers to it. Add my next idler, it goes up by idler drag. Add my next one, it goes up by idler drag. I just keep plotting my way through here, adding driven rollers whenever I approach the upper limit of my design range, and then starting over in the next span near the bottom end of the design range. And so I can do this all the way to the end. But there's more. Once I've gone through and done my tension plot here for all of the spans, what I would like to do is go back and model it. Okay, now you can build a simple model in Excel, and so it's not hard to do. You've only got the 4 formulas there. But what you can do with this is you can go back and ask what if changes. What if I change the modulus? What does modulus variation look like? What does my dry speed variation look like? How much variation is there in settings? How much variation is there in idler drag? Coefficient of friction? Any other property of interest that you have that might change? You can do your what if testing and go all the way through here. There's a lot of things you can look at. And you do this, you can pin some tolerance bars on your tensions. Now, hopefully, when you get through all of your what-if testing, none of your tolerance bars go above your failure criteria or go below your lower failure limit. Okay, if they do, now's the time to make the changes on paper and not do it in the machine after it's built. And so you can do all of the what-if testing that you want to do now, and all of the variation testing and all of the what are we going to do if this happens testing at this point. Now, one of the questions you're going to get asked is, what do all these driven rolls do for me? Okay, why don't I just have one at the end of the line? Well, if you do that, you're going to end up with a tension plot that looks like this. And if you add your normal variation on that, you're going to end up with something that looks like this. And what's going to happen is you're going to have a line that runs good web on a good day, but can't run everything. And so you're going to have some really bad days. And so you want to make sure that you can run everything most of the time. And so you want a web path that's going to look like this. With variation and not like this. And so you can justify driven rollers as a way of avoiding downtime and doing the what ifs. And you get this, you can adjust it as necessary. You can say, wow, I had some more leeway in here. Maybe I can space out another roller. Maybe I can adjust my design range a little bit. And you can optimize your web path based on what you think you can get away with. Now that you know what strain and tensions you want in every span, and that's exactly what you've done here. So I now know I want the tension and strain that you want at every driven roller. You know what you want to have set on your load cell or your dancer. The last thing you've got to do is go plug those values back into your strain transport formula, and you can calculate the speeds of those rollers. So, do you have any questions? Again, my contact information is given here. I'm happy to answer any questions on this presentation. You can reach me at ronjlynch@hotmail.com or at my mobile number there. Leave a message, and I'll be happy to get back with you. Thank you.